Alright guys, we are picking up where we left off in class about atomic radius, ionization energy, electronegativity, and electron affinity. Again, remember, electronegativity and electron affinity are two different ways to measure something that's similar, but one is a relative measure, the other is a true energy that's there. So it's a numerical assessment that has used through instrumentation, where the other one is a relative assessment based on behavior of atoms. Okay, so we were talking in class about ionization energy. Right, so I have to flip to this view in order to get me to be able to write on everything that I want to write on. Alright, so we were discussing ionization energy, and we were looking at the chart below, and we were talking about how you see it go up, then it comes back down, then it goes up, down, up, down, up. And I said this has to do with filling. And if you look at, this is the first row, this is the second row, this is the third row, and then this is the fourth. So here's our S's, and then these are our D's. So even in your D's you have a little bit of that pattern, and then you go back to the P's, right? So these are D's, these are P's, this is S, this is fourth row. Okay, so this filling has to do, this pattern has to do with the filling. So we start off with the 1S, or the S, let me say, and then you go to P. So if you look at these two, I said this was lithium and beryllium, and then when you go here, you're going to boron. Now boron, that dip, the dip in IE, going across left to right in boron, or for boron, is because you go to a higher shell. They go farther away, higher E. Okay, so that's important to note. That's an explanation of what happens. And then it goes higher, higher, and then on this next one right here, which is where, whoops, went a little big on that arrow. Okay, that's oxygen. So for oxygen, you have a second electron in an orbital. So that gives you electron pair repulsion. They ask you these questions in AP, not in Regents. They could care less in Regents because they don't even do the wave mechanical model. But they'll ask you, why do you have a change in that trend? Why does it go opposite the trend? And that's because now you have two electrons in the same orbital, and you now get negative and negative, and they're repelling each other. So there's a force pushing them apart, and once you hit them with ionization energy, it makes it just a little bit easier to get that electron out of there. Okay? So that is going across a row. Now when you go down a group, the general thing is that ionization energy decreases going down a group. You have more energy levels. This is an energy, not a little electron. Okay, more farther, outer electrons are farther away. From the nucleus. So the electrons experience less Coulombic force. Less nuclear pull. Okay, there's too great a distance. Coulomb's force we're going to learn is this formula. Well, there's an attraction and there's a force. Okay, now I got to remember. Q1, Q2, those are charges over distance. And you know, sometimes your distance is squared. So as this gets larger, the attraction goes down, easier to pull away. Less attraction. Okay, now, it says up here, that why does the trend happen the way it says, and then says, oh, well, you have to use this as an explanation. The radius decreases, holding electrons more tightly, so it takes more energy. Really, you need to say that you have less distance, greater Coulombic force, more nuclear pull. Whoops. Now this is a time where I'll say to you, it's probably better to memorize the explanation while you figure it out. You will truly understand this explanation as we get to the end of the course. But for now, for those of you who are great at memorizing things, you may want to just say, okay, I'm going to memorize the explanation so I can regurgitate it back in an explanation of why does the ionization energy go up as we go to the right in a row, and go down as we go down a group and deeper into the periodic table. Right? More nuclear pull. And actually, it's called more effective nuclear charge. But the best way to say, you know, you have more Coulombic attractions. Okay. On the other end, let me change my little pen color here so I'm not constantly writing in the same color pen. Here's that electrons, and this should be a lowercase e. This is not energy, this is an electron. An electron is further from the nucleus, not held as tightly, and smaller effective nuclear charge. And actually, this is not really correct. It really should change this. Somebody else had written this slide, and that's not. Small effective Coulombic force. Less Coulombic force. Or attraction. You can say Coulombic attraction, Coulombic force. Okay? There's the net nuclear pull is less. Distance is greater. Right? So just remember that. Okay. I'm going to erase everything on here, and we're going to go on to the next slide. It's kind of weird because in order for me to really write nicely, I got to do this weird thing where I've got to take the whole screen and put it into a screen snip so I can write all over it. Okay, so now we're going to discuss electronegativity. Electronegativity was measured by Linus Pauling. He actually got a Nobel Prize for this. And Linus Pauling was a chemist that worked at Stanford University. Linus Pauling was one of the people who had the rare occasion to have two different Nobel Prizes. He actually also, if I remember correctly, attained the Nobel Peace Prize. He failed at gym, though. He had to repeat it to graduate at Stanford, even though he was a ROTC. So for those of you who say, I don't do well at something, that doesn't dictate your whole future. You make your future what it is. You decide whether you will succeed or fail. I know a lot of you go like, yeah, but it truly is what happens. You can set your mind to something and work really hard if you love it. I know when I hated English, to write something was just torturous, and it would take me forever. And it is a state of mind. If you embrace it and try the best, it pays off in the end. Okay, a little side there. All right, so I'm going to snip this. Alrighty, so we're looking at electronegativity. Electronegativity is measured on a relative scale. So again, this is a relative scale, and it's relative, and it is set so that fluorine is a scale of 4. What Linus Pauling found while he was doing all his work was that fluorine always ended up with the highest amount of electrons around its nucleus. So whenever fluorine made bonds with anybody else, fluorine ended up with an electron density. Okay, it was like a little map of it. So I had anything with it. So I had sodium and I had fluorine, which was fluorine's a little tiny atom. All the electrons think fluorine was really cool and hang around fluorine. So then they occasionally buzz. Oh, sorry, we're going back over to the cool dude. And so he had all this electron density around him, really high. And no matter who fluorine was with, including xenon and was it krypton?
Yep.
Krypton. Okay, these are noble gases. Fluorine fools them. He's like the good old gesture of the court, but he's really smart. And he fools them and dupes them out of their royal electrons and takes them. And that's the only time those two, because they're noble, will ever make a bond is with fluorine. So Linus Pauling just set the scale to 4 and said fluorine has a number of 4, meaning it always ends up with the electrons. As you get closer to fluorine, you get closer to the number of 4. So it says move across a period and it increases. You're getting closer to fluorine. This is how you predict the trend. And I just use En to abbreviate electronegativity. En goes up. All right. Those elements closer to fluorine like to gain electrons to fill its octet. When it says to get more stable, it's not necessarily stability. It's an energy thing. They give off energy when they gain an electron, so they fill their octet. In the outer shells, the S and P, they give off E, big E, energy, so that's being stable. You don't have to put energy in, they are stable. Okay? As you move away from fluorine, so you move down the group, so if you're moving down the group, you are moving away from fluorine. Let me pick something that's going to show up. Yeah, I'll go back to it. Okay, so this moves away from fluorine. No matter where you are, you're moving away from fluorine. Oh yeah, we gotta do that. I don't know how we're gonna do this. I usually make you guys dance in class to remember these things. And I'm trying to figure out how to get you to dance if you're remote. I may make you get up and dance anyway. Okay. Why does this happen? If the electrons are farther away from the nucleus, it's harder for you to hold on to the poles. So if you go down and you look at like cesium, because it's readily available. Right. So cesium is a large atom. Relatively speaking, compared to lithium. Right, it's in the 6th row. Right, so if I say here's my nucleus, I've got 1, 2, 3, 4, 5, 6 of these wonderful little orbits, if we want to call it that. So I'm at a bigger distance here. Less Coulombic attraction. So if I'm trying to bring another electron in here, there's no pull. This guy's like, woo, I could go all over the place. There's nobody holding on to me. I can go all over the place. When you have fluorine, really tiny atom, and it's got everything in there, the little electron comes close and it goes whoop, and it starts going around there because there's electron pull. Right? So the farther the distance for your valence electrons, the outer shell, the harder it is for something to hold on to it. So the trends that are shown there are, if you go, this particular trend is going across. This is across rows. Doesn't show you down a group. But going down a group, it goes down. Right? And we might do an activity if we have time of graphing. I don't spend a lot of time on it because in AP you don't have the table to go to graph. In Regents you do. But as you go down, you'll notice if I go down a group, so this is increasing atomic number in a group. My electronegativity value would start at like 1.1, and you notice it would start to go down, and it kind of levels off a little because of just the measurement. Because over here, especially in group 1, when we're at francium, it's radioactive and it doesn't really. And actually, we can do hydrogen. Hydrogen's even higher. Hydrogen will be up there because hydrogen's 2.1, lithium's like I think 1.0. Okay, there's a table. I gave you a table and all that stuff I handed out, and there's a table in your book. And I forgot what page it's on. Okay, look up in your index, electronegativity values. Go look at that table and look at the trends. Okay, again, fluorine can take it. Fluorine likes electrons. Everything's relative to fluorine. So when you look at your periodic table, if an element is close to fluorine, it'll have a much higher EN value than something that's far away. Okay, we're going to revisit that because that's actually really, really important as we go on. All right, so that's electronegativity. These are down a group. So that's sorry, not down a group, that's atomic radius. But what's shown there is across a row. If you want to look at down a group, you got to go into your book. Okay, so now let's talk about atomic radius. Okay, so in atomic radius, oh, I didn't get the very bottom of it, but that's okay, it'll still work. Sorry about that. In atomic radius,
please dismiss first run bus.
For atomic radius, as you go across, again, this is across the row, and down a group makes sense, right? So down a group, we shouldn't have any issues with down a group. If you have a group, and you're going down a group, right, as you go down here, your principal energy levels get bigger, right? They increase in number. That means how many energy levels are there. So your E levels get higher. So you have greater distance from the nucleus, so your radius gets bigger. What is difficult for people to describe and explain is going across a row. As you go across a row, so you're going this way, right, your radius goes down. And the reason has to be with more coulombic attraction. Greater effective nuclear charge. I should probably pick another, yeah, because you can't see it. Let me go change my little color there. Okay, now you might say, well, what does that all mean? Well, as you are, if you have the atom and you're at, and I'm just going to do it by saying, you know, I've got an orbit here, and it's not really an orbit, and we have different shaped orbitals, but you're about a certain distance, so this is an R value, a distance. Now, in here, we're adding and adding and adding protons. So in the nucleus, you put a proton in, an electron comes out here. Put another proton in, you get another electron. Put another proton in, you get another electron. Put another proton in, another electron, etc. as you go across. Now, the number here is going up, the number here is going up, but this R, you know, what happens is you've got more attraction. There's more positive, there's more negatives, and so because this outer level can't be any further away from that, all of a sudden, this starts to pull these guys in. And they get closer and closer and closer. You know, they start getting in, and then it gets in a little further, and in a little further. So because you have more nuclear charge on the same distance going across, same E level, it pulls the electrons in. All right, and that is that greater
walkers, drivers, and riders.
Nuclear coulombic attraction. Right, more positives, more attraction. Okay, so that is atomic radius. Now we're going to get to electron affinity. Electron affinity. Now this one's weird because electron affinity is how much energy you need to essentially shove an electron into an atom. Now, understand, this is hard for some people. If your energy is positive, it means you had to put energy in. To get the electron to stay. Okay, if your E is negative, energy is released. When an electron is added. Okay, so really what that's kind of saying is the change does this. The change makes the atom unhappy. This here, the change makes the atom, if we want to personalize it, happy. I do it to the kin of, sodium or any of the ones in the group 1, and even to an effect group 2, but more group 1. Okay, because group 2 you get a little bit of a decrease in E that you have to shove into there because you have a filled s orbital. And then, it's like this sort of happy place. But if you want to take and you have, your electrons, and there's one electron there in your outer level, and there's only so many protons in here. Right? And then what normally wants to do is it wants to get rid of this and go down a level to be noble. Okay, now there's an electron out here that wants to join, and this element, any group 1 element, is I really don't want to have an extra electron. I don't want it, 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 I don't want it. And in order to do it, all of a sudden you got to almost whack it really hard and go, we're going to essentially force this electron into you. So it's almost like I have enough of my electron mouths to feed. I don't want any more. And the state goes, we'll pay you. So they pay them in energy. So E is positive. We're paying you. On the other end, so this is going to be the left side of the table. Okay, when you go to group 17, they want electrons. They want to feed more mouths. They want to adopt more kids, right? So think about, this is a horrible thing to say, but think about adoption process. You want to adopt a child, you pay money to adopt a child. So they want to adopt an electron, right? So they pay with E. Energy leaves. They're happy to get another electron. So happy, we'll pay you energy. So the energy leaves. Okay, there are these weird trends because this has to do with filling. Think about how we fill our electron configuration. Okay, so hopefully nobody got those wrong in the quiz because you had your notes and you could look up the order of filling. So I expect the quiz grades to be higher than normal on a filling question because you had your notes. But this is where it comes from, right? If we look at group 2, group 2 is filled. And we're going to go to a 2p, and it goes up to a higher E level. So it doesn't take, I still have to put in E here. You have to add E. But to add E there is less than the E to do this. To add this one in, this E is less than the E to add that in. Because you're going out. I know you might, well, but you're going to a higher energy level. Yeah, but it's a difference in E. How much E did it take to get this electron in here? Okay, so you have drops if you're going to be, if you're an element in group 2, you get a little drop because you have to make a change. If you're going group 2 to group 3, your E goes up. I guess I probably just confused you with that explanation, but here, let's look at it this way. Right? If I have 1s, and then I have 1, and I go to put another one in, I have an orbital that is complete now. If I go to the next one, right, to go from here to here, I have, so in this one I have E pair repulsion. So to put one in when I only have 1, so if I only have 1, I have a 1s and I have 1. And this is anything, let's say it's sodium, okay? And I have 1 there. To go to this, which would be isoelectric with magnesium, I have to add a lot of energy in. If I'm calcium, which already has 2, to go here and go up a level, this amount of E I got to put in is less than the E to go like this, from sodium to be isoelectric with magnesium. Okay, again, it has to do with filling. Group 12 is less because you've got a filled d orbital. Group 15, you have half filled sublevel, and then you're going to go into the next level. So if you're putting one in to do electron pair repulsion, you have to have more energy. If you're going up a level, it actually is comparatively a dip down in the energy. Okay, so just keep that in mind. It's kind of weird. Kind of weird to think about that. All right, let's look at the next thing. Nuclear charge and nuclear shielding. Now, you really don't have to calculate effective nuclear charge, but how you do this, and you'll see Z effective. Z effective is effective nuclear charge. It really is based on your number of protons and that you have. So this is your number of protons. So this is like your total number of protons. And so it's a difference between your number of protons total and the number of core electrons. So you got to be careful with the Z effective. In other words, it's looking essentially at your difference, almost like your valence number, but now it's positive because you're looking at how many protons are left to hold on to the electrons that are in your valence shell. Okay? So if your Z effective goes up as you go to the right, okay, and that Z effective pulls in the electrons. But I think a better explanation that they look for is about coulombic attraction. Okay, so if this relationship of how many protons you have to how many electrons you have, that's Q, Q1, Q2 has to do with charge. Over your distance, this would be the attraction. Okay, and then this is, I know this sounds stupid, but this is the force, if I remember it correctly. I always get them confused, to be honest with you. I have to go back and look it up. Right, so the R squared would be the force. I believe in R is your attraction, because your force is per distance, and then they do some more math to it. Okay, so the larger this number gets, the larger this is on the top, and the R stays the same, you have more attraction. Nuclear shielding is something that we only discuss it as you go down a group. Okay, don't discuss nuclear shielding going across a row. Is there some? Yeah, a little bit, but not like when you go down a group. When you go down a group, it's like, here's my nucleus. Again, for lack of a better way to draw this, we use our orbits. That's close. Then you got electrons there, and you got electrons at this distance, and then you have your outer shell, right? All these electrons inner here are a buffer zone for the guys on the very far outside, right? They shield them from the nucleus. Okay, nucleus can't see them anymore. Right? There's electrons in between. They run interference in a sense, like a buffer. And that's shielding. So as you go down a group, shielding increases. The more shielding, the less hold on outer electrons as shielding increases. That's another reason why ionization energy goes down as you go down a group. It's another reason electronegativity goes down. You can't bring another electron in and want another electron if you can't hold on to the ones you already have. But radius goes up because you can't hold on to the ones outside. They're farther away. Okay, so even nuclear shielding down a group can explain a lot of the trends. So the next slide has in it a summation, right? And we're going to have to do our little dance, and I got to make sure I find the video for this. It's something that maybe your parents might like because they might have remembered watching this movie, although I think we're getting to an age where your parents are too young, and it's called Saturday Night Fever. Okay, and there's a particular dance in there we're going to use, and we're going to apply it to remember the activity series. Now, general trends. As you go this way, right to left, electronegativity increases because you're getting closer to fluorine. And I'll change that pen color. Here's fluorine, right? This is 4.0. As you get closer to that, numbers go up. Francium is like 1.0. It might even be 0.9. So look at the difference. This is the most active metal. This is the most active nonmetal. Okay. If you want to remember radius, radius starts small, gets bigger as you go down a group. Oh, I've made like a snowman, and I have a mean neighbor, and the neighbor comes over and knocks my little snowman over after I've made him, knocks him to the right. My poor little snowman's lying on the ground. So as you go this way, your radius decreases, and this is radius. It only works for radius, not for the other ones, right? Knock the snowman over to the right. Okay, for reactivity, again, fluorine, most active nonmetal. Francium is most active metal, and technically we really key in on cesium, and the reason why we key in on cesium is francium is so little in our Earth's crust, it's very hard to get, and it's radioactive, so we don't really use francium at all. They actually looked into it a little bit in World War II, and then they realized there wasn't much around. It makes a huge explosion. It makes a good shock wave when you react it with water, and they thought they could use it in the Pacific Islands because there's so much water, but then they realized there isn't hardly any francium around, so you can't really build any bombs with francium. And lastly, but not least, because this is also important, what happens when you make an ion versus the atom? And we'll talk about this a lot when we talk about bonding and distance and more Coulombic forces. Okay, in general, I always speak in generalities because remember, the exception to the exception of the rule. Right? Metals will lose their electrons. They become positive. Okay, so this is an equation that represents it. We have one minus charge coming off. It starts 0. I get a positive charge for the ion. If I look at the charges here, I got a +1 and I got a -1. If I add those together, they will equal 0. I started at 0. When I do this, think about I'm losing something. If I lose something, I become smaller. And it's smaller because think about my balance. More P than E. So the protons pull the electrons in. On the other side, it does the opposite. I'm going to gain electrons. I add one in. So here's chlorine that's neutral as an atom. There's a 0 charge there. I'm going to add a negative, and look, I have a -1 here. So my total charge there is -1. My total charge here is -1 because I got an electron, it's got a negative charge. I'm adding in, so I become larger. So think about it. Same number of P, but more E. With the more E, it's like can't hold on to them. So your radius increases. Ion is bigger. Okay, that's the explanation. Alrighty. That is it. Hopefully you've got it all annotated and you're all good to go. Ask questions tomorrow if you have any, if you need me to go through anything, because I'm going to assume that you've processed this, you understand. So the thing that I want you to do in your packet is the only sheet that goes along with this. I'm finding it. Where did you go? 21. Page 21, and actually there's more that go along with it. Let's do 21, and we'll stop there. 21, because you had a lot to do with watching the video and taking notes.